So in this video we will analyze the associated wave of the electron. As before, you should have seen the earlier videos, previous videos, to understand exactly the behavior of the electron and the scenario. So we start with an electron emitted by some interaction. In this case, the electron will come out with its rotational axis a bit in any direction compared to the velocity vector of the electron. So we know from magnetism that the electron has an inherent force in the direction of its rotational axis, which means that the electron will not only have a velocity vector, but it will also have a transverse force which will deviate the electron from its mean trajectory. This means that the electron will have some sort of curvature, and if the electron has some sort of curvature, then you have a modification of the electric field lines, let's say around the electron, which leads to a concentration of the field lines on the inside of the curvature, and at the external part of the curvature the field lines will become sparse. This means that you create some image charge in the internal part of the curvature, which we can express in the same way as the longitudinal velocity that you can get from magnetism, and you can express this in the following way. So now let us see if we rewrite this equation as equal to the centripetal force of a classical particle in movement. Then you have this equation, and this you can resolve, and you get that the angular momentum of such a movement becomes a constant. This means that the trajectory becomes a spiral, as you can see in this figure, where you have the wavelength of the path is on a cylinder where you have one wavelength, and you have rho as a transverse radius of the movement. And this, as you see, is equal to, should be equal to the fine structure constant times lambda. Sometimes the Planck's constant. Now, if you look at the frequency of the transverse spiral, this should be, of course, be equal to the longitudinal frequency of the associated wavelengths. Then you can extract the fine structure constant from this equation, which then becomes that the fine structure constant is equal to the transverse velocity divided by the mean velocity of the electron square. And you can further develop this, and you obtain the reduced constant of Planck equal to this. As you see, this first expression is a classical one, and the second term is Daon Theory's expression for the same thing. From this we can also extract the transverse velocity and the radius of the transverse movement. So this is quite clear, comes immediately from the angular momentum. And you should also understand that the electron itself, when it's moving straight forward, gets a rotation of itself in the left-handed sense, while the spiraling trajectory of the electron can be right-handed or left-handed. There's nothing which stops this behavior. It can be both. You should also notice that the angular momentum of the electron becomes integer. That is to say, it's a perfectly classical behavior of the electron when it's by itself. Of course, you usually speak about integers, half integer spin of the electron, and this happens inside an atom. When the electron is free outside, then the spin becomes 1 equal to 1, whichever spin is really just the angular momentum effect. Okay, so we are now ready to start with atomic physics, which is somewhat more complicated. Okay.